I'd like to start by welcoming everybody. And we'd like to start by doing an activity we call a Chalk Talk. And the way a Chalk Talk works is we have a question up on the board. What do you want to know about ACA II's math program? So our hope is that over the course of the presentation we'll be answering most of these questions for you, and then at the end, if there's anything left that we haven't answered, we'll answer it directly at that time. So we are going to be talking about how our program bridges from each of the levels, from primary, elementary, intermediate, middle, and to high school and beyond. And one of the common threads that runs through all of those grade levels is our curriculum is aligned to the Common Core standards. And for some people, there's a little bit of negativity associated with those words, Common Core standards. And so we wanted to explain a couple things to help you understand. As Mrs. Dubitsky has frequently said, we were doing Common Core before it became Common Core. And let's think about why that is. So the Common Core standards are a guideline for teachers for what to teach. But in no way do they tell us how to teach it. Or they don't tell us how we should assess it. So a lot of times the confusion comes because people see these test questions that people have written for the Common Core and they say, these are crazy test questions. Why are we doing this to our students? But that's not what the Common Core is. The Common Core is a list of concepts and procedures that the students should be able to do. So one thing that's important to know is our school is research-based. The things that we do, the way that we teach, the instructional strategies we use, the way we assess things, those are all based on research. And the Common Core standards for mathematics are also based on research. There's a 100-page document of all the research that was put into deciding what standards are at each grade level. And those research-based practices, because we're also a research-based school, line up very nicely. So a lot of what was already being done in our program was what the Common Core asked us to do. So the Common Core standards ask in mathematics for students to be able to do three basic things. One is, this is what's new right here. This is one of the main differences compared to what the old standards were. And that is that students have a conceptual understanding of the math. So in other words, it's really important that the students understand why math works. That it's not just some mysterious abstract thing out in the universe that we're asking them to memorize. There's meaning behind it. This is a piece that Montessori built, and we'll talk about this a lot. This is a piece that we've built into our programs because it aligns with research, and Ms. Dubitsky will talk about that in a bit. But this is the piece, chances are, when you were going to school, you might not have had this conceptual understanding piece. And this is often where parents are saying, I don't know how to help my child because what you're doing with the blocks and the golden beads and all these different things, they don't match what I learned. Chances are what most parents learned in math are these two areas. So this is fluency with procedure. This is, for example, being able to say your math facts really quickly. This is being given a long multiplication problem and knowing, oh, I multiply this, and then I put a 0, and I multiply this and this. That's fluency. So this is something that comes with repeated practice. And then the Common Core also asks for application to solving problems. And all three of these are equally important in the Common Core. So I think it's important to understand that for us, with our philosophies and our research-based practices, we already have these three things built into our program. So when Common Core came along, we were great, we're already doing this. We're asking our students to be able to think critically, to understand what they're doing, to be able to not just be given a page of worksheet with, here, multiply these problems, or here, divide these fractions, but to be able to understand in context when it's appropriate to use each of those types of operations to solve a problem.
You learn best by having different tiers of experience. The very first one is being their experience. So that's why we go on so many field trips, a lot of study trips, right? The same thing works with math. You need to have something concrete. You need to feel it, you need to be able to touch it. The next step is once you feel it and you touch it and you have that, then you can go to a 2D representation. You're drawing pictures of something. It's not the thing that you're holding in your hand, but you can picture the thing that you held in your hand because you already held it in your hand. Once you have that down and you don't need the 2D anymore, then you can go to abstract it. Too many of us, when we learn math, we always went straight to the third one. It's like, okay, then you put the 0 on the bottom, and then you do the thing with the thing. We didn't understand why. In my classes, Ms. McCutcheon and I were just talking about this, we get these like, oh, that's why, all of the time. It's like these huge light bulbs go on for the kids because they understand the reasoning behind it. So we start, especially in the younger grades, with everything is 3D and concrete. So you see here the geometric solids. As they move up in a concept, they're going to 2D because they don't need this part anymore. Once they have the 2D and they don't need to draw it out because they can picture it in their mind, they can go to abstraction. Now the beautiful thing is this happens not just from K to 8, but for every concept we go through. So the younger they are, the more you see 3D. If they're working with a concept later on, same concept, let's say multiplication, in maybe the end of elementary or intermediate, you're going to see 2D, and then by the time they get to middle school, they don't need it for that concept anymore. They can be in abstract, and they can just do the formula because they've gone through all of the steps. However, if they learn something new in middle school that they've never seen before, they're going to start back here with 3D. They're not going to go straight to abstraction because it's proven by research that you have to start everything that you do with 3D. So they're still manipulatives in intermediate and middle school. They just look a little bit different than what you're used to with the Montessori materials.
So let's talk about how this process, which Ms. Davidsky mentioned, is woven throughout our entire program. Each time there's a new concept, we go back to concrete or semi-concrete to help the students understand that concept before moving them to abstraction. Let's talk about what that looks like at each level.
As Montessori said, when the children are young, like until 6 or 7 years, their brain is like a sponge. They absorb everything. So we need to expose them to hands-on, like for concrete. Like that's why in preschool and in kindergarten, we are asking children to go to Montessori to have that concrete ideas, whatever it is, the language or math, or anything for sensorial, anything they have the concrete. They touch and feel it, and they say, okay, this is cube. Okay, this is how the cube is, and this is ovoid. So they have that feeling. So which builds into the second one, the intermediate, the semi-concrete. So Montessori have a base for the children to move on to the next level.
And then once you get into intermediate, like we said before, there's a lot of things that they did early on in their Montessori K-3 career that allows us to build on those concepts. Every time, though, we introduce a new concept, we're breaking out all of the materials and we're starting over at the 3D concrete level. Our job is to make sure that they're using whatever they have learned in 3D and then we're turning it into 2D. So there's a lot of picture drawing and boxes and arrays and representations on paper in intermediate. You start to see at the end of their intermediate years, that's when they get into more of the abstraction with concepts that they've been working on for their entire academic career. Because they've taken the time to go through 3D concrete materials in the Montessori K-3, then they've done 4th and 5th grade in 2D, and now they're moving towards abstraction, getting ready for middle school.
So starting in 6th grade through 8th grade, students use a curriculum called College Preparatory Math, which is CPM, which has been around long before Common Core, in fact. And it is based on the idea that students need to develop ideas conceptually so that they can then transition to being able to do them abstractly. It's also based on the idea that it's really important for students to be able to explain their thinking. So it's great if you can solve this problem and tell me the answer is $73.55, But if you can't explain why you did that or how you got that answer, then there's a piece that's missing that still needs to be worked on. Because that's the part that lets you transfer your skills to new situations, which is what we want when we get out into life, right? You don't have somebody over you at your job saying, oh, this is a multiplication fraction problem. You don't have that. You have to figure out, based on the skills that you have, whatever it is, whether you're, trying to shop for a party or plan a fundraiser, whatever math skills you're using, you have to be able to apply those to the context of whatever the situation is. A lot of times with CPM, it's a little scary for parents because it is a lot of words, a lot of walking through students through a process of figuring something out. And until they have that chance to figure it out, it can be a little confusing for them. But as Ms. Dubinsky mentioned, those aha moments happen so often in this classroom where students will just like, oh, I get it. I understand why this works the way it works. And that, to me, is one of the best parts about teaching. Because it helps them to remember what it is that they. Okay, other questions about that bridging?
Oh, well, I just wanted to know how much time, or is there a fixed time frame that you guys work on a daily basis dedicated to doing, the bridging and all of that math level, or?
I think that's a different answer for each level. So do you want to start first?
So, sorry, I didn't get
Oh, because, Lily always on her goal book, it says, I did math, I'm going to do more math. Like, every day I go, honey, there's got to be more. That's why I'm like thinking, do you just do math every day, all day? Because that's all you have on your goal book. So, is there a fixed time that you guys do it?
No,
or?
we don't. No, we have the contract, and in that contract, they have like 8 jobs to choose from per week.
Yeah.
So they get to choose, and we have like Monday, Tuesday for each day. So they get to choose. We ask them to do language arts, math, science. So they get to choose. And we notice that the child is doing only math job, then we also encourage them to do, oh, I noticed there are only math jobs checked in, so let's go back to language arts. So we always notice that, and we ask the child to go back to other jobs too.
In intermediate, it kind of varies on the group. It's broken up into a lot of different parts. So Monday, Tuesday, Wednesday, and depending on some of the groups, Thursday, they have at least a half an hour dedicated direct instruction from teachers in math. Then based on the grade level, they may have, like 4th graders are going to have more practice with math facts than 6th graders are, because the 4th graders need to have their multiplication memorized in order to make CPM easier once they get to 6th grade. So we spend 15 minutes 4 times a week on just math facts. Then they're going to have 3 independent assignments that they have to do, which could take them anywhere from like 15 to 45 minutes, depending on the complexity of the task and what they're being asked to do, and if it's a group job. So we're averaging about 4 to 5 hours a week per grade level in math right now, but it really depends on the student. It depends on which group they're in. It depends on the week. So it's very flexible, but it's at least 4 hours.
And when we get to middle school, we have an hour rotation for math, or an hour and 15-minute rotation for math. And some kids finish their work in less time, and they're able to switch and do something else, or work ahead in the curriculum. And some kids need longer. They need to sit down with me for an extra 30 minutes to help figure out their homework. So it's one of the nice things about our school is that the answer isn't the same for every student. It's based on what the students need. All right, so here's a problem that 8th graders had to do, learning how to solve equations. And I just want you to take a look at what the students need to understand abstractly in order to conquer a problem like this. So they have to know how to add, how to subtract. They've learned how to find a missing number. They've multiplied. They can use the distributive property. They understand what a variable is. They understand what negative numbers are. These are all concepts that are embedded into a problem like this, that by the time they get to middle school, they can work fluently on adding, subtracting, things like that, multiplying, they don't have to think about it anymore. That's automatic. That's like driving the car. You don't have to think about, I need to turn my turn signal on. It just automatically happens. That way your brain can focus on the new task of solving this equation. And so that is our goal, that by the time they've moved up the levels, they've increased the number of skills that they're able to do fluently, and then can apply that to the new concepts that they're learning. So what we'd like to do is give you a little taste of some of the things that we do hands-on, and I don't know if this counts as tutoring for parents, but to give you an idea of what kind of understanding you can get from having a picture or something like that. And we'll start with
the golden bead. So in Montessori, units are shown with a nice little golden bead. It's so cute, it's so little, it's golden, that's why they call it the golden bead. There's a lot of them in here. All of these represent 1 unit or 1 in base 10. When you have 10 of them, they put them together in a tens bar, okay? It's really important that you see that all 10 of the beads are there. They have literally taken 10 golden beads, stuck them together on a wire. The kids can count them. It's not abstract. This is extremely concrete, which is one of the really, really, really big cornerstones of Montessori. The kids understand that this is 10 because they have taken 10 of these beads with holes in them and stuck them on a wire. Like, okay, I understand that. As opposed to like one of the base 10 bars where it's like cut out and you can't really see that it's the actual unit stuck together. Then you move on to 10 of these is 100. Now they have taken 100 golden beads and placed them on a rack. And now you have your nice flat hundreds. And so in primary, they deal with all of these golden beads. They start with the units, they go to the tens, they go to the hundreds, they go to the thousands. And they can hold 1,000 beads in their hand and they can understand that it's 1,000. As opposed to, like, let's say one of these guys where it's just, they can see it on the outside. Oh, okay, they really do believe that there are 1,000 in here.
All right, so let's try the stamp game.
So this work, the children, they don't need to know their multiplication facts because they will not be there yet, still they can use it. So the problem is 3,221 times 3. So since we are multiplying 3 times, I'm going to use these pegs. 3 times 1 time, 2 times, and 3 times. So I got 3,221 3 times. Now I'm going to add all of them together. 3 units. 6 tens. 100, 200, 300, 400, 500, 600. 1,000, 2,000, 3,000, 4,000, 5,000, 6,000, 7,000, 8,000, 9,000. The answer is 9,663. So before the Montessori method, when I was learning, I need to know the math facts, I need to know the math tables. But this one with concrete, the ties and numbers, so the children will be able to do it.
I noticed one common misconception in the older kids is that we're still just doing 3 times 3 is 9. But we're not. We're multiplying 3 groups of 3,000. And so this really helps with understanding when I'm multiplying 3,221, it makes sense that my answer is in the 9,000s and not just a random 9. So they really have that understanding very well by the time they've gone through this program, understand what is behind the math and why it's working.
So now we have 100, we have 4 tens, we have 4 tens, and then we have all of these units. So theoretically, 14 times 14 should meet all of that, should equal all of that. So let's figure this out together. We have our 100, we have 40, we have another 40, and then 4 rows of 4, 4 times 4 is what? 16.
now I'm just gonna add those all together.
196. Okay? Once we get to this part, we're going to do something else with them. We're going to teach them what the distributive property looks like, how to break apart a problem in smaller pieces. So like you see on your paper, that was just times 10. You start with just times 10, filling in the arrays. Then,
I heard a question,
okay.
and I don't know if you answered it, but they said, why are the 4 going this way and these 4 are going this way?
Yeah.
If you picture this like area,
Mm-hmm.
an area of a rectangle, the width of this rectangle, if we break it apart, is 1, and the length of this rectangle here is 10. So that's why it goes this way. Because this, where is it, this 10 block?
Is length times
10
width.
block has this is 1 across and this is 10 long. So it matches. When I say I want this to be 4 long, this is the end that has to make the 4. 1 plus 1 plus 1.
Oh, I get it.
I will show you with area. Watch. Okay.
Length times width.
14 times 14. I'm multiplying my area. So I'm taking this guy. I don't want 14. He's too hard to deal with. I want 10 and 4.
Oh, okay.
I don't want 14. He's too hard to deal with. I want 10 and I want 4. So now I'm going to break it apart in 10 times 10. 10 times 10 equals 100.
Oh, that's
Wait for it. Okay. Now this guy times 10.
I see it.
Okay. This guy times 10.
I'm a kindergarten
4.
teacher.
And now I'm left over with 4 times 4, where I have 16. So now that they get this, and they start doing it, and they're just like, they're like, why does that part look like that? But they have to do this part with the actual 3D materials first, before they can get to this and then just draw it. Now we're at the position where they are taking numbers when you have 14 times 14 and you're breaking it apart. So I'm going to take this 14 and break it up into 10 and 4. 10 times 14 equals 4 times 14 equals. Okay? If I needed to, I could break it down even further. I could break that 14 down into 10 and 4. So then we had all of those multiplication problems that I just saw. So you would be doing 10 times 10, 10 times 4, 4 times 10, 4 times 4. But we don't need to do that anymore. We're here. Okay, we can manage this pretty well. So now I have my 10 times 14. 140, because I took my 1 times 14 and stuck a 0 on the end. Then 14 times 4, they know very easily because they did the stamp game, and now they're at abstraction with that kind of multiplication. So they can just do the old 14 times 4, 4 times 4 is 16, put your 1 up there, 4 times 1 is 4 plus 1 is 56. So now they're adding them together. Look at how much more manageable that is than this nonsense. Then when you add those together, you end up with the same answer, 196. You have just taken apart a problem. They call it breaking it down, but it's the beginning of the distributive property. So what they've basically done is taken this problem and turned it into 10 times 14 in parentheses plus 4 times 14 in parentheses equals something.
Let's take a look at algebra tiles, which we do start using a little bit in 6th grade, 7th grade, 8th grade, and it's my understanding that the Antioch Unified School District is using CPM in their high school programs, so they'll continue with algebra tiles. You can do all kinds of amazing things with algebra tiles. So the ones we use in 7th grade and 6th grade were for simple solving equations. We're going to look at 2 kinds of tiles. So you should have one in there that is a rectangle that is turquoise on one side and red on the other. Okay. So if you find that one, and you have the teeny tiny little square, I'll tell you what the other ones are, but we're only going to use these 2 kinds today. Sorry, so this is a unit tile. Just like the base 10 system, this represents 1 unit. it is like a golden being, right? And they have that understanding. This can represent 1. But what do we do? Or I'll show you my picture here. This is 1. It has a length of 1 and a width of 1. So the area of this tile, 1 times 1 is 1. Okay. This tile we use when we have a number. We represent a number that we don't know. And in math, a lot of times the letter we use to represent an unknown number is x. So if you line these up, you'll notice that, I'll switch to here, the width of an algebra tile is 1, but the length here, if you try to line it up, it won't line up. And that's on purpose, because it's representing a number that we don't know. And we don't want the students to think, oh, this is 3. It's not. It represents an unknown number. Also in middle school, we start learning about negative numbers. So the positive side is represented by the blue. The red side represents -1. The same with the algebra tile, the x tile. The red side represents the opposite of our unknown number, or negative x. To solve an equation, we're going to think of an equation as a balanced scale. And I have balanced scales that we could pull out and use, but it's going to take a long time. So I have a computer simulation. You all know, if you've seen a balanced scale, if I put something on one side that's greater than the other, what happens? The balanced scale tips. To keep it balanced, I have to have the same thing on both sides. Well, an equation there's an equal sign in the middle. It's telling me what's on the left side is equal or equivalent to the amount on the right side. So if I'm going to do a difficult one to start with, 2x, plus -5 equals 1. That means I'm on this side of the equation, 2x plus -5 equals 1. One side of my equation has 2x tiles, plus it has 5 negative tiles. Does that make sense so far?
Yeah.
The other side of my equation has what? 1. And you're probably thinking, what? How can that be balanced?
No.
It is. It's balanced.
I don't believe it.
So now we have to figure out what value, what number would make this balanced scale true. So in order to figure it out, we learned multiple steps for this. But in order to figure it out, we have to think. We can add the same thing to both sides, and we can take away the same thing from both sides, right? That's how a balanced scale works. To keep it balanced, we can put the same thing on both sides. We can take away the same thing from both sides. So, I'm going to go back to the concept of 0. I'm going to get these x tiles all by themselves. So do I have something on both sides that I could take away? Something that's the same I could take away? No. But I could add the same thing to both sides. What could I add here that would make 0?
5-1.
Yes. So I'm going to add a 1 over here, and it makes 0. So in order to keep it balanced, I have to add a 1 to the other side. Make sense? So I'm putting a 1 on this side, making 0, putting a 1 on the other side. Putting a 1 on this side, putting a 1 on this side.
This is the coolest computer program.
Yeah, we're sliding it when I was in high school.
So when we're finished, we have, what's left? We have 2 x's is equal to 6. So what do we do at this point? Well, I think here, this isn't going to let me line it up because I worked ahead. But the idea is I can divide these x's into 2 groups, and I can do the same thing here. I can divide these units into 2 groups, and I can see that this x is equal to what amount? 3. And this x, you can ignore that stuff in the middle, is equal to what amount? So x equals 3. A problem like this, we can still use the algebra tiles, and it's not so scary. I mean, I can do it if you want, but it's not so scary because they're familiar with it. I think it's important to understand we're showing you the concrete, but if you remember, we talked about earlier that we go through this process with everything that we teach them. So we get to the abstract eventually. This is what we've shown you today is concrete. So this is where the students start, but not where we finish with them, if that makes sense. We do get to this point, to the point where they can just solve the equation and just write down what they're doing in the steps.